Hello everybody, welcome to video 10 of STA 513. Let's go ahead and get started. I'll jump to the share screen and get you guys right to this chapter. Now this becomes part 3 of FUN 513, and what we basically want to do again is just bulk up what we've done before. So again, to date, we've done the one-way ANOVA, and like I said, from 512 to 513, we really bulked that up with a lot more extensions with respect to confidence intervals, contrast, multiple comparisons, estimate statements, and all that. And we did the same thing with the two-way ANOVA. Then we threw the analysis of covariance component into the mix. In this part 3 of the course, we say, well, why stop at 2 factors? Why not bulk it up even more if we want to? In the cocaine study that you guys can see with the with respect to the project, is that, well, in that case, we have a lot of different measures. We have treatment, site, gender, race, just a whole battery of different measures, where a good number of them happen to be categorical measures, such as treatment, the 4 treatment arms, which consisted of individual drug counseling, cognitive therapy, supportive expressive, and group drug counseling. The site with cocaine study, there's 5 sites, which include, Penn, WPIC in Pittsburgh, MGH, it's Massachusetts General Hospital in Boston, McLean, and also up in the Boston area, and then and Brookside, which again is also in the New England area. So 5 sites. Gender, the male, female, and then the race was coded as Caucasian, non-Caucasian. So we have those 4. So, with the previous chapter, we can look at treatment by site interactions, which is really whether or not the treatments across the differences across the 4 treatments, whether or not that varied or was differential across the 5 sites. And we fit that, and you could fit that and make an interpretation of it. Namely, if that was significant, that would basically say that treatment comparisons vary as we go across those 5 sites. And you can see it as being either ordinal interaction or disordinal action. Obviously, the mean profiles can help assist us in deciphering what that interaction meant. But we could easily have done this where we extended it to gender. So now that would be the differences across treatments varying across sites, whether or not that behaved differentially across the 2 genders. So again, are the differences between treatments that we see across sites, do they behave differently between men and women? That's a treatment by site, by gender interaction. It's a 3-way interaction. And then we can easily extend it to a 4-way interaction. Treatment by site, by gender, by race. So are the differences we see between treatments that vary across sites, which are different between men and women, are they different across Caucasians and non-Caucasians? Obviously, the more we bulk up the interactions, the little bit of a tongue tire that it begins to become to interpret what's going on. So with the multi-factor studies, the multi-way ANOVA models, it really becomes a balancing act of truly fitting the data, modeling the data, and the story being told by that model. The most tightrope kind of walking that you have to do as statisticians is to be able to communicate the model. So you have to be aware that you could fit a really complicated model, but if you can't explain what that model is doing, then the complexity is not worth it at all, right? So it really becomes whether or not you can explain it in terms of what it means. Because again, like any regression model that you guys saw in 512, if you throw the whole kitchen sink into the model, the R-squared will go up. But if you can't explain what the model is saying, then the model is basically worthless, you know, in a sense of trying to get what's going on. For me, you know, the most complicated model I ever dealt with ended up being, you know, a five-way interaction, and actually on this data, but using different measures, which really looked at the treatment by site, by gender, by race, by alliance. And this alliance measure quantifies how well of a relationship the patient has with his or her therapist. And so what we saw was the treatment differences, which varied across site, which varied between men and women, which varied between Caucasian, non-Caucasian, behaved differentially depending on whether or not people had high versus low relationship, that's the alliance measure, with their therapist. Obviously, the complexity becomes one thing, and the way to kind of be able to tell the story of the model is to be able to visualize it. Well, that's going to be one of the components we want to do. For what we need to do in this intermediate linear models class, we'll kind of build the models all the way up to a three-way ANOVA. You know, just a three-way ANOVA for what we need to do, but obviously you need to be aware of four-way, five-way, and hopefully some of the visuals that we end up showing you can kind of help you get prepared for the multi-way ANOVA models. But in this case here, the big thing with the three-way ANOVA, when we think about it, representing it, is that the amount of representation gets a little bit more complex, as you would expect. And with the complexity, you know, what we could see here is that now we still have the outcome Y, that's still our response variable, but now we have three factors, factor A, B, and C. Now factor A, like the example we were just looking at, treatment, that has up to I levels. With cocaine study, that's 4. Factor B could be something like site, which for the cocaine study is up to 5 levels. And then, you know, the third factor is like gender, which in this case would have 2 levels. So now we have these three subscripts, I, J, K, I representing the level for factor A, J representing the level for factor B, and K representing the level for factor C. And for us, the observation will be represented by the IJKL subscript. And with the L, it really just shows the Lth observation in cell IJK. And there is no reason to assume that the number of observations per cell, now remember, a cell is determined by its level on the 3 dimensions, factor A, factor B, and factor C. There's no reason to assume that the cell size across all the possible combinations are the same. You know, from an us perspective, you know, nothing really, you know, it doesn't really matter whether they are or they are not the same. You know, the software, SAS, R, STA, SPSS is all going to be going through the derivations ourselves, you know, itself, and kicking us out the results. The big thing is, you know, any kind of software package is going to accommodate the unequal cell size and give you unbiased, robust estimates for the respective parameters and the inferences as well. So from an us perspective, nothing really changes. If we go to the cell me model, the big thing we have to remember is in this three-way ANOVA, we're going to fit the main effects of A, B, and C respectively. So just like in one way, these deviations, kind of like what we saw with the tau parameters in chapter 16, you know, the sum of the alphas, the sum of the betas, the sum of the gamma or deltas, they will sum to 0. So again, that's one of the constraints. Then we have the respective two-way interaction components. So in this three-way interaction model, we need the interaction of A and B, A and C, B and C. And then again, remember with the three-way interaction terms, the coefficients will sum to 0. you know, whether we have when we have one of the dimensions held fixed and we sum over the other dimension, these deviations will sum to zero. So again, remember we have the sum of the alpha betas over I when J's fixed sum to zero. And then similarly, the sum of the alpha betas over J when I's fixed sum to zero. That's true for each one of these three. Again, when we're working with estimate statements, you know, obviously, and contrary statements, you know, that could get to whether or not you could, quote, simplify those forms of the equation. Whether or not you recognize that phenomenon's going on, yeah, really doesn't matter. You know, SAS, Stata R will capture that, you know, that component in the model really is zero. And you don't really need to be weighted down by remembering all of those nuances. And then the last term is the three-way interaction, the alpha beta delta, where again, you know, just kind of like what we just saw, when we sum these coefficients, for example, if we sum these coefficients over k, where I and j are fixed, they'll sum to zero. If we sum it over j with I and k fixed, it sums to zero. And if we sum these coefficients over I with j and k fixed, it sums to zero. Again, this really just gets deviations from the mean. You know, as we saw in 505, 504, when you sum deviations from mean, they sum to zero. And that's what these parameter constraints on the respective cell mean models getting at is, again, you know, here's the grand mean, and anytime we have an I fixed or a J or IJ fixed, you know, anytime we have a single dimension level fixed or two dimensions of the three fixed, we're talking about either a row or column mean for the first case or a cell mean. And anytime we're summing deviations around that mean, deviations around the mean by definition sum to zero. So as we just said, you know, these constraints are really looking at the deviations of the respective cell mean, whether the cell means JK, IK, IJ, those constraints will sum to zero. Again, it's just, again, deviation summing to zero. We can go, in this case here, to cell mean model layout if we want to even make it more simplified. And then again, this is going to be residuals. Residuals. Now I'm using the M to represent the observation within the IJK cell. Yeah, so that's the mathematics, really in essence, the vector matrix layout of what's going on. The estimation model works just as we saw in one way, just as we saw in two-way, just as now we see in three-way or multi-way. The first thing we have to get after is estimating the cell mean. And estimating the cell mean is nothing more than the sum of the observations within that cell divided by the number of observations in that cell. Right? Just the raw mean is our best estimate of the cell mean. You know, so again, our best estimate of this guy, of this cell mean, is the sum of the data in that cell divided by how many we have. And that's represented in this formula here. Then for each cell, we can get estimated variance within the cell. And then for us, the pooled variance is going to end up equaling just the deviations within the cell squared over the number of observations at cell minus one. Obviously, when we get a cell size of 1, that cell will not contribute anything to estimating the pooled variance. Right? And again, with the estimation of the pool variance, our estimate of sigma squared there is going to be the MSE of the model, the mean squared error. The mean square error. So again, this model handles, you know, all parameterization. If we have a cell size of 1, Yes, we will be able to estimate the model. When we have a cell size is 0, this is where you're going to see the degrees of freedom are not going to behave. And then you have to really decide whether or not fitting the complicated, in this case, three-way model is, is appropriate in trying to decipher a three-way interactive relationship. So again, you might have to think about making it a reduced model, whether it's a one-way layout or a two-way layout with a FADA, remember FADA, one factor at a time, kind of combination of the respective cells. So again, we pull those sample variances where each sample variance, each cell variance in this case, is weighted by its degree, its number of observations in that cell minus 1. And then the pooled estimate follows this formula where we end up getting the weighted sample variances, or I should say really the weighted cell variances divided by, our total sample size. But again, that's all that's going on in the background. So now, that's just fitting the model. But one of the things we want to check out is a three-way interaction present? So if you recall, when we examined a two-way interaction, we focused on the graph. And with the graph, we looked to see whether or not the graphs crossed or whether or not there was a differential spread for differences across one factor as a function of the other factor. So in other words, we were looking for either whether or not there was an ordinal or disordinal appearance in the graph. And again, the ordinal appearance is, okay, the deltas are in the same direction, but vary in magnitude. And then the disordinal was a crossing of the graph. So we're trying to see that behavior. Well, that was a good way to flag a three-way interaction. Now, for a three-way interaction, there's a couple ways to do it. The book walks you down this first approach, and I'll show you a second approach that I think's a little better. But with the book's approach, they say, hey, with a three-way interaction, can we, in essence, we would need a 3D plot, which could still be a little confusing to visualize entirely the three-way interactive behavior. But the book says, hey, can we reduce one of the dimensions? And one of the dimensions, can we reduce the dimensionality of the model graphically by one dimension? And what they do in that one dimension is they say, well, instead of looking at the cell mean, maybe if we look at the delta, the on average difference between levels in one dimension, and graph that in a two-dimensional space. So get the delta as a function of one dimension, and that really works well if one of the predictors is binary. If one of the predictors is not binary, it becomes a little bit more complicated. So I think the approach I'm going to show you after the fact may be a little better. But if it's not binary, then you have to create a series of graphs for each possible delta. So again, if we had a variable that was 4 levels, so think about how many deltas you can create. So that'd be 4 choose 2, right? Which would be 4 factorial over 2 factorial over 4 minus 2 factorial. So that ended up being 6. That ended up being 6 deltas. So that would correspond to 6 graphs that we'd end up getting. But let's go ahead and take a look at this example. I think when you see this example, you're going to see how my graphical approach perhaps works a little better. I think it works. I think visually you'll see what's going on. So we're going to jump to this, chapter 24, page 1005. When I take you to this in the book, right, so I'm in the chapter 24 book, which, anytime this has happened, in the textbook, you notice, you know, if I'm copying the book, if the one page, you know, obviously when I took the book apart, you know, it was front and back. So anytime the front page of one page was the end of the previous chapter, I make sure page 2 is the beginning of the chapter. We want to go to page 1005. So let me jump down to 1005. Here's 1005. So in 1005, we want to look at this example here, trying to see where the problem. Okay, cool. Here it is here. So now in this case, we have 3 factors in the model. The first factor is gender, obviously male, female. The second factor is body fat of the subject. And then the third factor is smoking history of the subject. And here we're trying to measure exercise tolerance. So the outcomes Y is exercise tolerance that we're looking at. And if we go back to the data, I think the data was right up here. So in this case here, we have their smoking history, which the smoking history is going to be light smoking versus heavy smoking. I guess in this sample they have a group of people with a smoking history. With the fat, it's talking about their diet. So whether or not it's a low fat diet or a high fat diet. And then with gender, we got 1 equal male, 2 equal female. So that's our data there. So let's go ahead and go back. Let's go to SAS. So let me go ahead and open this as we proceed forward. And as I open this, let me get to you guys. So we're going to chapter 24, page 1005. Okay, I'll go ahead and put the nums on the side. So we're going to load the data up. So here's the Y, here's the gender, here's the fat, here's the smoking. So let me go ahead and just load this up. Right, so not really a lot of observations. So print it out, right? So we end up having, what's this look like, 3 units per cell? No, 3 units. Is it really 3 units per cell? So we got 3, 2, 2, or is it 2 units per cell? It looks like 3 units per cell. So we got the 4. My fault. Yeah, it's 2, 4. It's 8. So 8 by 3. So 24 observations. So that's cool. It's cool. Again, I could have went right here. So as we see, 3 observations per cell. As we begin here, I'm just going to get what I'm doing here is I'm getting the means per cell. You know, so on the first, from line 45 to 60, I'm getting the means per cell. So this is showing us the mean exercise tolerance for, in this case, this first cell is males with light smoking history and low fat diets. And then if we go here to this last one, this is females with high fat diets with heavy smoking. So we got the respective cell means. So that's cool. That's cool. So now I'm trying to create a graph that represents the 3 dimensions. So in this case, this red one, I'm reducing the data set just to the males. And with the males, I could use a rename statement or whatever. I'm just creating the mean for males as a new variable, mean extol 1. So this is the mean for the males. So I got 4 cells now, the 4 combinations within men. I do the same thing for the women, right? So that creates menic style 2. Now I'm going to combine these 2 data sets. So I'm sorting them first, could use proc SQL, but I'm going to use the merge. Right now, remember, these data sets are sorted, so it's exactly the same layout: smoke, fat, fat iterating within smoke. Here, with them being exactly 4 rows, with each row being the same combination of gender, my fault, of smoke and fat, I don't need a by statement. I could throw the by statement in the mix just to be safe, but in this case, I will not. Right, so in this case here, this is going to show us the mean difference between men and women for each of the cells. So in this case, you could see the difference between men and women with respect to exercise tolerance. Now, it was male minus female. So within the light smoke, low fat, it's a 6.13 difference. Low fat, high smoke, 7.7 difference, right? So within the low fat, it looks like the difference between men and women is consistent over levels of smoking. And then for here, for the smoking, for the heavy fat, the on average difference between men and women's 2, and then almost 6. So now it looks like the difference between men and women varying over smoking status, right, does not appear to be the same in the heavy fat diet, but does appear to be the same in the low fat diet. So now this makes me wonder whether or not the difference between men and women as a function of smoking status, whether or not that's behaving the same as a function of low or high fat. So I'm thinking this. Now let's take a look at it graphically. And obviously this is just dealing with the means. One thing, as the model starts getting more and more complex, showing the raw data on top of each other can kind of get make the graph a little busy. But now, when I look at this graph, you're looking at this graph where, again, the one dimension's difference between men and women. Now think about this. It's almost like, in this case, to determine whether or not you're having a 3-way interaction, look at this difference graph and say, does that look like a 2-way interaction behavior? Because if it does, if we're going to call this a 2-way interaction, and in this case, it'd be an ordinal interaction, because the on average difference here appears to be of different magnitude here, in the same direction, but a different magnitude. So in this 2-way interaction, we're asking ourselves, does the on average difference between men and women as a function of low or high fat diet, does that behave differently over levels of smoking, right? So the difference between men and women, differing between low and high fat, appear to be somewhat different between light smoking and heavy smoking. Again, the fat's the line, the x-axis is smoking. So we say, so this could be a possible 3-way interaction. When I see this, obviously they're not running parallel. One thing to keep in mind, we don't have a lot of data to really view it. So I'm beginning to wonder whether or not that's the case. But now I think this may be the better way to look at it visually. In this case, I'm doing the plot separately for men and women. Separately for men and women. And I think it might look better if you look at the plot this way, using the SG panel layout. So in this case here, look at the difference between low and high fat varying over smoking, and look to see, does that two-way interaction plot we see for men appear to be different from women? So does the two-way interaction between fat and smoke, does the two-way behavior between fat and smoke, does that appear to be different between men and women? And it's kind of like, I do see this delta is pretty big, this delta is pretty small. This delta is pretty big, this delta is pretty small. Now that behavior seems to be similar. So these two shapes don't look dramatically different. The thing that's different about them is that for males, it looks like exercise tolerance, for those with a heavy fat diet, it looks like there's a slight increase in exercise tolerance from light to heavy smoking. Whereas for women, it's a decrease. So maybe that is the potential differential behavior. But I'm beginning to wonder, is that really, could that possibly just be some sort of gender artifact? Right away, I know that there's an issue with respect to fat. You can see the blue, regardless of gender, is always above the red. So I'm expecting a fat main effect, right? And then similarly, when we look here, when we look with respect to, smoking, if we collapse, as a function of fat, it looks like the mean for smoking might be a little different for the groups. So maybe there's a smoking effect. Gender-wise, I don't know. It looked like if I got the mean for those four combinations, maybe a slight effect for men, slightly higher than women. But right now, eyeballing it that way, I don't see that the two-way interaction within males behaves differently than females. A slight issue with the red line, but nothing dramatic. So in this case here, let's go ahead and fit the three-way interaction model. So now when we get here, line 135 and line 136, remember, they're doing exactly the same thing. Line 135, this is the factorial layout of the model statement. So when SAS sees these vertical lines, you're telling SAS, fit the main effects, fit all two-way interactions, and fit all three-way interactions, which is right here. Again, line 137, outputting the predicted values, the residuals, the jackknife residuals, the standardized residuals. And then here, I'm trying to decipher what's going on. So again, remember the slice command kind of give us some of the issues going on with the contrast. So if I'm going to go ahead and go here and fit this model, this one's going to create a lot of output, and that's all right. So let's go to the top of the output, not to make you dizzy. Right, so we go right here. Now, remember, this is saying at least one of the terms is significant in the model. Jump to the three-way interactions. Our whole attention goes here. This is where our attention goes. Your attention goes to the highest ordered model, right? So in this case here, we could say, now remember, regardless of the significance of these terms, if the three-way interaction is significant, all the components of it stay in the model, right? The two-way interactions, the main effects, they all stay in the model. So anytime you have an interactive term, remember, the higher order terms stay in the model. So in this case, we see based on the available data, we do not have sufficient evidence indicate a significant three-way interaction between gender, smoking, and fat is predictive of exercise tolerance. Therefore, based on available data, we do not have sufficient evidence in our data to indicate that the on average difference between men and women, varying as a function of diet, behaves differentially as a function of smoking level, right? So we have no evidence of that. So what we see here, I didn't think it was going to be a three-way interaction, and that is what the significance is telling us, that we do not have evidence of a significant three-way interaction. That is that the on average difference between men and women varying differentially as a function of light and high fat, low and high fat diet behaves differentially between light and heavy smokers. So now, from a perspective of parsimony, we would remove that three-way interaction from the model, and then proceed forward. In this example, each of the cell size was equal. So again, that creates the orthogonal design we saw back in the two-way models, namely in chapter 19, where the cell sizes were equal, as opposed to chapter 23, where the cell sizes were not. In the orthogonal design, the type 1 and type 3 sums of squares reproduce. So namely, when we're focusing on this, we could see a smoke by fat two-way interaction, a fat main effect, a smoke main effect, and a gender main effect. But we do not see a gender by smoke two-way interaction, a gender by fat two-way interaction, or the three-way interaction. This is giving us the cell means via the Ellis means command. Again, you could do the pdiff, tdiff, adjust equal Tukey, adjust equal Schaffe, adjust equal Bomfer, and you say everything we did before directly applies to this setting here. This starts coming into the slice command. So we got this here, and we got this here. So now the gender, smoke, fat effect sliced by gender for exercise tolerance. So you can see these three, so within males, we have a highly significant effect. Within females, we have a highly significant effect. But what does this mean? What does this mean here? Well, if we go back to our panel plot, what that slice is doing is within males, we have 4 means. That slice is testing whether or not the null hypothesis, whether or not the 4 means within males are equal. And the bottom one's whether or not the 4 means within females are equal, right? Whether or not these are different, whether or not any of these cell means differ, remember in that case, that's really not telling us anything specifically about the interaction behavior. What it's basically, what we're getting here is, in this case, these 4 means being different can be a combination of the gender main effect, the smoke main effect, the fat main effect, the two-way components. We don't know. And actually even could be part of the three-way interaction. But just remember, that slice is looking at these 4 cells. Now it could be helpful, right? With these 4 cells, saying, okay, at least one of them separating from the pack. We know it's really, in this case here, the low-fat, light smokers are, have on average the highest exercise tolerance, whether we're talking males or females. That might be what's going on. But again, remember the slice. So the way we worded it was gender, smoke, fat. So again, we go back to the syntax. It was, in this case here, it was line 139, gender, smoke, fat, slice, gender. That's just really getting at whether or not one of those 4 cell means is differing within men and similarly within women. The LS means reproduce again, and they reproduce again for this line. The gender, smoke, fat, slice, gender, smoke. So if we go here and we look at this, the gender, smoke, fat, sliced by gender, smoke. So if we go here, you can see in these cases, we got 1 degree of freedom, 1 degree of freedom, 1 degree of freedom, 1 degree of freedom. Let me go back up to the plot we just have, right? So if you look at the first one, the first one is, ends up being gender, smoke. And if we go up to the plot, I'm going all the way up to this plot here, right? So we're looking at gender equal 1, smoke equal 1. So namely, that slice is looking at this on average difference. So namely, is the difference, is the difference between, is there a significant on average difference? It kind of works with respect to the plot. Is there a significant on average difference as a function of low and high fat diet for, in this case, for males with light smoking? So that difference right there, that pairwise difference that we see there, gotta go with it, is highly significantly different. Highly significantly different, right? So that's the p-value 0.0002. And then if we go across the board as well, go back up to here, the second row is 1, 2. Gender 1, smoke 2. So gender 1, smoke 2 is looking at this on average difference. So is there a significant difference between low and high fat tolerance, low and high fat diet on average exercise tolerance? This contrast we saw below, that had a p-value 0.1439. So we see a significant difference here, a non-significant difference here. Non-significant difference here. We go down to the 2-1, right? So if we go down to the 2-1 again, and we look at this, this is significant. The 2-2's not, right? So we jump back up to here. This is saying, within females, the on average, based on the available data, we have sufficient evidence in our data to indicate a significant difference within females on exercise tolerance for those with light smoking as we go differentially between low fat and high fat diet. Whereas when we go to heavy smoking, the on average difference is non-significant. So this behavior, significant, non-significant, significant, non-significant, that almost sounds like there's an issue with respect to smoking that we end up seeing. Again, the blue line over top the red line, that almost sounds like in this case, there's a fat issue. And then similarly, as we look across, males, females on average seem a little bit lower compared to males. So in this case here, these 3 main effects we see here, right? We do see within both genders, there does appear to be a smoke by fat interaction. That is, the on average difference between low and high fat behave differentially between light and heavy smoking. where it's significantly different for the light smoking, not significantly different for the heavy smoking. That behavior is consistent whether we're talking males or females. That consistency gets to this smoke by fat two-way interaction, but no three-way interaction. So this slice command we saw here kind of helped, helps tell the story of what's driving the two-way interaction and what's not driving the three-way interaction. We could do the same thing with the gender by fat and the smoke by fat. So if we drop down to this one, so in this case here, gender, smoke, fat, sliced by gender, right? That was what our initial one was. Gender, star, smoke, star, fat, sliced by gender, smoke. We just looked at that. And then this one is gender, smoke, fat, sliced by gender, fat. So in this case here, with the gender fat, we got the 1-1, which is significant. We got the 1-2, which is not significant. We got the 2-1, which is significant. And then we got the 2-2, which is not significant. So now let's keep an eye on this 0.0264. So if we go back to our plot up here, so this is gender fat, right? So we're looking at the gender fat, where gender fat's 1-1, right? So in this case here, that contrast, that slice here is going, okay, here's, in this case, we're looking at the on average difference across the blue line, right? So the 1-1 is looking at this mean compared to that mean. So as we're dealing with males with a low fat diet, we see a significant on average difference in mean exercise tolerance for those with light smoking compared to heavy smoking. When we go to the 1-2, this is the difference across the red line from here to here. So we see a non-significant difference between, for males with high fat diet between low and heavy smoking, right? Significant difference, non-significant difference. We get to the females, so that 2-1 contrast at a p-value 0.0071. So similarly for males, we do see a highly significant on average difference in exercise tolerance for women with low fat diet between those with low and heavy smoking, right? And similarly to the males, we see that those with the light smoking had higher on average exercise tolerance compared to those with heavy smoking who had lower exercise tolerance. When we get to the 2-2, so the females with high fat diet, we see a non-significant difference between those. So think about this. As we go within males as a function of diet, we see a significant difference in exercise tolerance going from light to heavy smoking within the low fat diet. That's the same as what we see for the women, but no difference on the high fat diet, right? So remember, the three-way interaction is the difference of differences of differences. And we're seeing similar behavior on these slices. This is significant, that's significant. Same for men and women. Non-significant, non-significant, same for men and women. Then when we get to the last slice, this is gender smoked fat sliced by smoked fat. So in this case here, we got the smoked fat 1-1, 1-2, 2-1, 2-2. So the 1-1 0.0257, the 1-2 0.4345, the 2-1 0.0069, and the 2-2 0.0327. So again, if we go back to our mean profile, the panel plot, if we think about this, so with the smoke 1-1, smoke fat 1-1, this is looking at this mean compared to that mean, right? This mean compared to that mean. So we see a significant on average difference in average exercise tolerance between men and women of whom have low fat, light smoking history. And then the 1-2, smoking 1, diet 2, this is contrasting this to that. So on that slice below, that was a p-value 0.4435. So we see, based on the available data, we have no evidence in our data indicating on average significant difference in exercise tolerance between men and women of whom have light smoking but heavy fat diet. Go to the 2-1, right? So now we're talking about the smokers. So the 2-1s, this blue compared to that blue, right? And we saw that at a p-value 0.0069. So now, again, based on available data, we have sufficient evidence in our data to indicate the significant on average difference between men and women is significantly different for those men and women who have heavy smoking, low fat diet. And then similarly, when we get here, the 2-2 is this mean compared to that mean. And again, and that had a p-value 0.0327. So based on the available data, we have sufficient evidence in our data indicate a highly significant, well, a significant on average difference in exercise tolerance between men and women of whom have heavy smoking, high fat diet. Now, all those slices, those differences, it's not necessarily telling us anything about specific effects. So any difference we're seeing can be a combination of the main effects of the respective variables, gender, smoking, smoking, fat, diet, or the two-way interactions, gender by fat, gender by smoke, smoke by fat, or the three-way interaction. So we don't know that through these slices. So with the two-way interaction, it really did assist us. In the three-way interaction, it could be a combination of a lot of things, and then you have to just really be careful of what we see. But nonetheless, when I see this plot here, the two-way behavior I see here is not significantly different from the two-way behavior there. So I think this panel plot does a really nice way of keeping all the dimensions so we don't have any differences. And really, for a three-way interaction, you're looking to see, are the two-way behaviors differential over levels of the third factor? So in this case here, we don't have a significant three-way interaction. Now, as I said to you guys before, I think the book's great. And like I said before, this is the book I used back in my graduate work. And, this is the book that you guys are using yours. But the one thing the book does is, hey, we're going to talk about three-way interactions. I'm going to give you an example where it's not significant. And it's kind of like, all right, okay, thank you, Mr. Book. But, I think to understand the three-way interaction phenomenon, it'd be good to see a significant three-way interaction. So line 148, I'm flipping the cell orders to create a three-way interaction, as you guys will see. In the model above, right away, that three-way interaction term is non-significant. So you really should go to a parsimonious model. So for me, we could see the output, and we're dealing with the orthogonal design with the cell sizes being equal. But for me, usually I don't have the cell sizes being equal. So in building the parsimony model, this isn't proc reg. It's not anything we could do any kind of stepwise approach to it. So what I do is I chop down this tree, basically one whack at a time. And so for me, I would take the three-way interaction term out, then fit the model. Look at the two-way components. Any of the two-way components non-significant, I would keep in. So again, if we were doing it